So I'm Patrick from TechwaY. TechwaY is a French company, European-based. We are focused on FPGA technology. We do our own FPGA systems that we sell internationally. And in Europe, we offer to our customers, European customers, third-party product in addition to our solution. Most of the product we rep for European customers are usually coming from US. Jerry, how? So I'm going to share today with you some facts and trends about high-speed serial links that we have been dealing with within TechwaY to serve our defense and avionics customer in Europe. As you know, our world was parallel. And I'm not talking about dinosaurs here. I'm talking about our world, let's say 15, 20 years ago. Everything was parallel. And I believe you all remember the VME when it was 32 or 64 bits. PCI came after that with 32, 64 bits. And what happened is we are all aware about the Moore law, which give us access to a lot of processing power. Processing power is almost available for the quantity we want for always the cheapest price. But there is an issue with communication, and powerful system can be useless if you cannot, if you don't have a means to push data in and out of it. It's an obvious thing, but for years and ages, system integrators has always struggled with communication bottleneck to make the best usage of the processing power which was available from the IC vendors. So dealing with high bandwidth communication links has been, and it's still a big issue, as of course everyone knows. So at the beginning, things was buses and communication links were parallel, and vendors tried to increase the bandwidth by enlarging the bandwidth. We had in PCI 32 bits, 64 bits, 128 bits, and then we tried to go faster. We all remember these buses being sampled at 33 megahertz, 66 megahertz, 133 megahertz. But each time we increased the bandwidth, we couldn't communicate on very long distances. And with a 33 megahertz PCI X, we really reached the limit, the technology reached the limit of what could be achieved with parallel buses. And of course, the next step to go forward was serial buses. And that's how I believe the PCI Express came up. Just you all have figures in mind, but if you make the calculation, you see that, remember that the 64-bit sample at 133 rates for a parallel bus gives us 1 megabyte per sec data bandwidth, when a 1 gigabit per sec serial link gives you 100 megabytes per second. So it was an obvious trend to increase the bandwidth. And as time goes, people have increased the speed of serial links. We had 100 megahertz Ethernet. We had 1 gig. We now have we have 10 gig Ethernet. And of course, technology vendors are working on 12, 30, even 30 gigabit per sec bandwidth. But as we increase the serial link bandwidth, we see also that to achieve higher bandwidth, we need to put many in parallel. So we had we have a PCI Express 1X, 2X, 4X, 8X, 16X. So again, we sort of loop we are making a loop here and coming back by putting even serial links in parallel in order to achieve a higher bandwidth. The FPGA vendor, the FPGA technology is the sort of main technology to deal with this high communication bandwidth. The FPGA vendor, as shown here on the graph, taken away from Xilinx literature, that in 10 years, more than 10 years, the number of high-speed serial links provided by the FPGA vendors have been multiplied by 6, and the data rate at which they operate have been multiplied by 5. So that's the difference that you can see on the diagram. So really the FPGA vendor have been very cautious in using the Moore's law and the always integrated capability of the technology to implement more and more communication capabilities on their devices, which makes these devices absolutely necessary to manage these high-speed communication links. And when it comes to FPGAs, we think about FMC, which is, as you all know, the mezzanine interface dedicated to FPGA technology. And we see that they today capture the FMC standard as it is today, capture pretty well the capacity of the FPGAs, because you have on the existing and available format up to 10 links, high-speed serial links, which can operate at 10 gigabits per sec each. So which is very well balanced with what the FPGA technology could offer so far. But as we see on the graph, that the new generation of FPGA will go much faster than that, and we're talking about 33 gigabit per sec for the new technology from Xilinx. It's an obvious thing that the FMC standards will have to evolve, and as you know, there are some current work within the VIDA committee to take that into consideration. Works. I'm going to spend half of my time dealing with that. We're in the technology.
Well, it says your time's up.
I'm saying. Just for information, wanted to recap some main pro and con of thanks, Jerry, of the technology. Obviously, the main benefit of serial that we all know is you can go faster, you have higher bandwidth, and you can go at a longer distance for your communication. But there are cons that we are all aware, but shouldn't be forgotten. The two main cons that needs to be outlined, we think, is the latency of the communication links, which is not too much an issue for backplane communication and system communication, but is an issue for real data communication, where people are extremely careful in some field about, of course, latency. So real-time data communication could sometimes be not compatible with high-speed serial link. Another issue is, of course, going faster, even on high-speed serial link, requires new technology for PCBs. Just for information, that the current PCB technology has limitation at 7 gigabit per sec, and to implement faster, high-speed communication, you would need to change technology and look for even new technology on PCBs. So today, as what we see is high-speed communication being used to implement backplane communication. We all know about VPX, for instance, which is one of the most popular instances of that situation. We all know about also high-speed front-end communication. For people who are familiar with FPDP, we saw this standard moving from serial FPDP. There are many communication, like Ethernet, of course, like even data, like Coax Express for image processing, which are using high-speed communication link to move data in and out of systems. But what we see also as a new trend and with upcoming technology on the market is high-speed communication being used for chip-to-chip communication on circuits. I put here 3 examples of that, of what we can see in that market. So we see high-speed serial link being used by ADC vendor, which wants to take benefit of a higher bandwidth to offer a solution for ADC that will be with the fastest sampling rates, ADC at 2 gig, 4 gig, 5 gig, 10 gigs, which are currently being launched by these vendors. Some of them are offered with high-speed serial link instead of parallel buses for communication. We see at the bottom, you will see you must be aware about the HMC protocol that will be for memory, the protocol coming after the DDR4, which is also a serial communication link. And so all these new usage of high-speed serial link are now offered to a board designer. Of course, protocol, the Vita organization is following, that is capturing these trends to offer a solution to board makers and system makers. We put here 2 examples of how things have evolved, both on the right for a protocol known as Vita 17, which is used to call the FPDP. At the beginning, it was a parallel protocol to move data in and out of a system, in real-time system, very well known by radar vendors. And it has moved to a serial FPDP, and this has been captured in an upgrade of the Vita 17 called Vita 17.1. And the bus becomes serial logic. And now the Vita committee is working on an upgraded Vita 17 protocol to take into consideration the latest news and latest capabilities of the high-speed serial link. Same for buses. I will not go through it. You all know that story. From VME to VPX, where we stand, and VAO, upcoming discussion to take also into consideration the latest capabilities of high-speed serial link. When it comes to very high-speed serial link, optical is a need. Optical is going to be mandatory. It's an obvious thing. But optical, in order to easily implement optical or take the benefit of optical communication for high-speed serial link, we need some technology, and we need some upgrade of the standards in order for this technology to be captured in some form factor. I gave here 2 examples. You know the VPX, form factor. And you have a board here pictured from one of our partners. And as you know, there are some more than work. There are some work done at VIDA to define the VIDA 66, which works in adding high-speed optical communication in addition to the VXS front panel backplane. So you see, even if the VXS backplane is a serial backplane, as you know, most of the time this backplane uses electrical connectivity. And if we want to take benefit of the latest technology in terms of communication, we need to go optical, at least for data, and adding an optical communication link to the VPX backplane is what the VIDA 66 is defining. So you have a drawing here of how this will be implemented, and I think we have other conference later on today that will explain that in more details. You also have, from the technology standpoint of view, a company offering a very integrated optical capabilities. And I present here the Samtec component, one of the latest Samtec components. It's a technology called Firefly. And we have picked up this technology to work on some high-speed communication boards. One of the key features of this type of component is that you have on a sort of a one IC up to 12 high-speed serial links that could operate, in case of this component, up to 14 gigabit per sec. So it's a highly integrated optical device, which is ideally suited to implement, for instance, VIDA 66 type of connectivity, or to implement very high density front-end connectivity. So together with Samtec and for the editors, we are issuing today a press release with Samtec about this product. We have designed an FMC which features this component that you see here, which has the capability to operate up to 10 links, receive and transmit at 10 gigabits per sec. And of course, as you understand, the limitation here is not coming from the component itself, which has, I think, 12 links and can operate at 14. The limitation comes from the FMC, but still, having 10 bidirectional links at 10 gigabit per sec makes it an extremely powerful way of putting data in and out of a computer. So the board, our FMC, is offered in two configurations. The top one shows a sort of a front-end type of FMC. The second one, the bottom one, shows a way in an embedded system to implement optical connectivity that can be used in backplane in order to move data inside the system, taking benefit of optical connection. And just as an example of what we have done with this type of technology, I don't know who this morning was saying that today the market is going for function boxes. But we have used the technology you've seen before into industrial form factor boxes to deliver switches to Airbus industry. And these are what we call ARANC 818 switches. ARANC 818 is a video on fiber channels. It goes at 3 gig per sec today. There is an upgrade of this standard to go to 6 and 8 gigabit per sec. And this standard is used on modern airplane by Boeing and Airbus. And our equipment have been used as test equipment by Airbus and HSFly during the certification program of the 350. So it gives you an example of how useful this high-density, high-speed serial communication can be. And as a collateral effect, it shows also how the VIDA technology can be used in some more commercial application. It was originally designed for defense program and finally used also by Airbus. So to summarize, having high speed, the need for high bandwidth, high speed communication is mandatory. I mean, it's an obvious thing, of course. Technology is addressing it. People like Samtec are offering, for instance, and they are not the only one, but are offering solution. It's important to have organization like VIDA to works to capture this technology trend and to offer form factors that can be used by the industry. And if we pick up the FMC standard, which we are interested in, it's a good example of what's happening. Today we have sort of a picture. The FMC standard, as it is today, has very well captured the state of the art, but needs to go further if we want to take benefit of the ultra scale, for instance, version of the Xilinx FPGAs. And I thank you for your attention.